Welcome to part 2 of neuroembryology for medical students. This episode is concerned with neurulation, the continuation of that theme, but we're going to have a look at the embryo at a slightly different angle. We're going to look down from the dorsal aspect, down through the amniotic cavity, onto that ectoderm now. So about day 19, and the notochord has already grown from the primitive node cranially underneath the ectoderm. And we can see the differentiation of that ectoderm into the neural plate here. It's the notochord that has induced that differentiation through signaling. So you can see here that at the cranial end, the neural plate is a lot wider than it is at the caudal end of it. And that's because that's where the brain's going to form, the cranial end obviously, and that needs more room. About the midway down the embryo, it's going to be the cervical area, and everything caudal to that is going to be the spinal cord. You can see here the neural crest has already started moving up, that's elevating towards us in the plane of the image, and they're going to try and contact each other as we saw in the previous episode. You can see it's in the neural groove stage here because you can already see a groove made by the movement of those neural crest cells. Day 25 here, we can see the primitive node marked there, which is the origin of the notochord, and the neural plate moves with the notochord as it's instructed by the signaling molecules that the notochord secretes. About 50% of the ectoderm is going to become neural plate, the rest of it's destined for epidermis. So we can already see some somites forming in the middle here, which is a concurrent process. Neurulation isn't the only thing going on at the moment. So day 28, anything past day 25 really, the neural crests are going to contact each other in the middle of the embryo first. That's where the neural tube proper has been formed now. And that's formed the neural tube, which is going to be the central canal in the future, and that's lined with ependymal cells. So from this area, which is the cervical area, middle of the embryo, this fusion is going to travel cranially, form the brain, the anterior or cranial neuropore, and caudally, the caudal neuropore. So about day 29 here, we'd expect the cephalic neuropore to close over to allow the brain to start forming, and the caudal neuropore will close about a day later. Because the evidence here of other processes happening concurrently, we've got sets of somites on the longitudinal axis on either side, and we've got a protuberance from the primitive pericardium also. Failure of either of the neuropores to close gives rise to some pathology, and we'll see that pathology in the next episode. It's worth noting here the disparity between the spinal cord and the vertebral column length. I say this because we've just looked at the embryo on a longitudinal axis and the neural tube, spinal cord. And the reason for this disparity is the vertebral bodies, the bone, grows a lot faster than the nerves can grow. So you can see here on the right hand image, the upper red arrow is at the level of the conus medullus in the spinal cord, which is about level L1, L2. The bottom red arrow is at the lower extremity of the vertebral column, the coccyx. So that's the difference in length between the spinal cord and the vertebral column. Underneath the conus medullus, so in between the two arrows, there's a large sac of dura which coats all of those individual neurons as they exit the vertebral column at whatever level that they're intended to. This is where lumbar punctures are used to penetrate the dura and sample cerebrospinal fluid. It's done in the lumbar area because as the needle goes in, it moves between those nerves instead of puncturing a large section of nerve as it would above the level of L1. I've distracted you there with some spinal cord, but can you tell me how old this embryo is? You can see some somites, and it's fused at the cervical area.